Welcome to learners to this lesson of technical sciences. Today we'll be dealing with physical properties and reactions of organic molecules. So without wasting any time, we'll move to our objectives of this lesson. At the end of this session, you should be able to do the following. You must be able to discuss physical properties, relationship, that is the melting point, boiling point, vapor pressure, and viscosity. In alkanes, alkenes, alkynes, haloalkanes, aldehyde, ketones, esters, alcohol, and carboxylic acid. So these are our 9 homologous series. So you must be able to know the melting point, boiling point, vapor pressure, and viscosity of these 9 homologous series. You must be able to compare the physical properties of different homologous series. So we're sticking with 9 for technical science. For a given homologous series, you must be able to explain the relationship between physical properties and the strength of the intermolecular force, the type of functional group, the chain length, molecular mass, and branched chain. Lastly, we will do the reactions of organic molecules. We're going to do esterification, substitution, addition, and oxidation. In our approach, I'm going to be teaching. At the same time, I will be giving you exam tips so that we will be able to know what is expected of you in the exam. Now, before we start with our organic molecules, I want to talk about water because everyone knows water. As you can see, the structure of water is given there. You are having H2O, which is indicated there. You are having 2 hydrogens and an oxygen. So in the structure of water of H2O, you are having the bonds, which are indicated on the structure, which you are able to see there. Those are the bonds. These bonds, we refer to them as covalent bonds. These covalent bonds that are found in the water molecule, we refer to them as intramolecular forces. They are intramolecular forces because they are found within a molecule. So this is a water molecule. Inside the water molecule, we are saying we are having forces. We refer to them as intramolecular forces, which use your covalent bond. However, water molecules participate in multiple hydrogen bonding, meaning that it is not alone. You have water joined to many other water molecules. So water is joined through hydrogen bonding, is joined to other molecules of water. So you are having water joined together by intermolecular forces. Now we're referring to intermolecular forces. So you will know that intermolecular forces is between the molecules as compared to intramolecular forces that are within the molecule. So for this section, we're not going to talk about intramolecular forces. We're going to concentrate on the intermolecular forces, which are the forces that are joining the different molecules of water or of our organic compound. So that is how the water is bonded to one another. Now, let's look at physical properties of water. Water, you know that it has 3 phases of water, which is the solid, the liquid, and the gas. So you can find water as ice at home, which is at a temperature of between -20 and -16 degrees Celsius. Now, when the water is solid, it's in a fixed shape, and it cannot flow. It has maximum intermolecular force. But when the water is in a liquid form, it's no longer a fixed shape. It's now no fixed shape. It can flow. It has less intermolecular force. I'm happy because we are always referring to the intermolecular force. So you know that the water molecules are joined together by intermolecular force. Now, as well, when we move to gases, they have no fixed shape. They can flow. As well, they have very less intermolecular forces. So you can see that in solid form, in liquid form, and in gaseous form, water will have intermolecular forces. What is different is the strength of the intermolecular forces. Now, if we are having intermolecular force, we need to overcome this intermolecular force in order for water to become liquid. So if you want to melt water, your ice, you must provide energy. Energy will be needed in order to overcome the intermolecular force. So we're saying for a solid to become liquid, what you will need energy in terms of temperature. Remember, temperature is the average kinetic energy of the average kinetic energy. It's a measure of average kinetic energy. So we're going to provide our water, which is in solid form, provided with energy. When we provide it with energy, the energy must overcome the intermolecular force. So immediately when the energy overcomes the intermolecular force, water will change from solid phase to liquid phase. So we're saying in our change, as we change from solid to liquid, what we need is the temperature or is the energy. Energy is needed to overcome the intermolecular force. So I want to emphasize that because the entire section of organic molecules in terms of physical properties will be looking at intermolecular force. We're saying to overcome the intermolecular force, you need energy. Energy is required to overcome the intermolecular force. If we have energy, we can be able to move from solid to liquid. Now, let's look at the process where a solid becomes liquid. We refer to it as melting. So it means when a solid becomes liquid, we say the water or the ice is melting. Melting is a process where the solid is changing to liquid. However, we have what is referred to as melting point. So there is a difference between melting and melting point. Melting point, however, for water is a temperature of 0 degrees Celsius. So you got to know that the melting point of water is a temperature of 0 degrees Celsius. As we indicated that in your freezer, you are having the temperature between minus 16 and minus 20 and minus 16. So obviously, you got to come with increased temperature until 0 degrees, then melting will take place, which is changing from solid to liquid. Now, what we are saying is that at the melting point, a melting point is a temperature where the solid phase and the liquid phase are at equilibrium. So we are saying at the melting point, we have both the solid phase and the liquid phase. Both of them are at equilibrium. So when you define melting point, you will say it's a temperature. However, be aware, you can't say melting point is a point. It's not a point, it's a temperature. That's one of the mistakes that learners make in the exam. They define it as a point. No, it's not a point. Melting point is a temperature. At that temperature, the solid phase and the liquid phase are at equilibrium. So you got to know that the solid phase and the liquid phase are at equilibrium when you are dealing with melting point. Now, when the water, now it means at the melting point, you are having the solid and the liquid. All of them, they are coexisting. You are having both the solid and the liquid. So you got to understand that at the melting point, you have the solid and the liquid phase that are at equilibrium. You have both of them. Now, when you melt your water, it becomes liquid. When you are having your liquid, we said it can now flow. It has less intermolecular forces. However, it still have intermolecular forces. It's just that it's less than solids. When you are having your liquid now, you can see your liquid now, the structure are no longer joined as they were joined together in the solid. So you can see that when you talk about liquid, you have overcame some of the intermolecular forces. Now, when you are having liquid, you start to heat the liquid. Obviously, the temperature of the water will start to increase. As the temperature of the water increases, you will see that there will start to be bubbles inside the water. So now that means that if you are having the bubbles inside the water, it means that now in the bubbles there is vapor. So vapor you start to have vapor inside your liquid. Now, when you are having vapor in the liquid, as the temperature increases, even the vapor is increasing. However, the vapor pressure that is inside the liquid is less as you start at the lower temperatures. But as the temperature increases, even the vapor pressure increases. So now, the atmospheric pressure in the atmosphere, not in the container, in the atmosphere, we're having atmospheric pressure of 1 atm or 101.3 kilopascals. So what we are saying here is that as the temperature increases, as you are moving that side, the temperature is increasing, even the vapor pressure is increasing. It is still less than 1 atm, however, it's increasing. At around 80 degrees Celsius, you'll be having a vapor pressure of around 0.7, 0.8, so they are increasing together. Now, immediately when you reach 100 degrees Celsius, the water will start to boil. Why is the water boiling? It's because the vapor pressure is equal to the atmospheric pressure. So I've talked about two definitions. The first one is the melting point. We said the melting point, we're having the solid phase and the liquid phase are at equilibrium. But when you talk about the boiling point now, we're saying the vapor pressure, which is the pressure inside the container of liquid, is equal to the atmospheric pressure, which is the pressure outside. Now, immediately when the water starts to boil now, we can now talk of vapor pressure. We said vapor pressure is the pressure exerted by the vapor that as well is at equilibrium with the liquid. So there are three important definitions. Remember, we're going to do 4 different physical properties, which is your melting point, boiling point, and vapor pressure. So you got to understand them. So we're saying at the melting point is a temperature at which the solid phase and the liquid phase are at equilibrium. At the boiling point, the vapor pressure is equals to the atmospheric pressure. And then vapor pressure, we said the definition of vapor pressure is the pressure exerted by vapor, which is at equilibrium with the liquid. Now, without any wasting of time, I've from the exam guideline, you have your four definitions, three definitions that I was talking about, which is the first one, we said is the melting point. So that's how you must write them. Remember, when you are writing exams, you must ensure that the definitions, you write them as they appear. So we are saying melting point is a temperature. I emphasize that. Melting point is not a point, it's a temperature at which the solid phase and the liquid phase are at equilibrium. So you can see that the solid phase and the liquid phase are at equilibrium. That is melting point. Now, what is boiling point? Still, boiling point is a temperature at which the vapor pressure of the liquid is equals to the atmospheric pressure. So Vp equals to AP, as I've simplified it for you. The third definition is the definition of vapor pressure, which we are saying this is the pressure exerted by vapor at equilibrium with its liquid in a closed system. This is very much important that when you define vapor pressure, you must indicate that this is happening in a closed system. Why closed system? Because if the system is open, water will escape the container as vapor. Then you won't be able to have your vapor pressure measured correctly. So we are saying here it must be in a closed system. We are saying vapor pressure is the pressure exerted by vapor at equilibrium with its liquid in a closed system. Lastly, our fourth definition is the definition of viscosity. Viscosity is the property of the fluid, this liquid that we're talking about, is the property of the fluid to oppose relative motion between two adjacent layers. So those four definitions are very much important for this section, which is your question 3 of physical properties. Now, without any wasting of time, remember what I said. I said for us to be able to boil, to melt, or to boil, or to have vapor pressure, we must overcome the intermolecular forces. So the first thing that we must know is what are those intermolecular forces. We are going to concentrate on 3 intermolecular forces, which is your London force. Your London forces is your first intermolecular force we're going to talk about. This London force are weak intermolecular forces. They are very weak between non-polar molecules. So they are found between your hydrocarbons, your non-polar molecules. As we indicated here, that these London forces are found as well in all the molecules. So all the molecules that we are having our 9 homologous series, all of them, they will have London force. So you got to understand that all the molecules will have London force. And we have indicated here the London force, which is the intermolecular forces. Remember, we said for this section that we are doing, which is physical properties, we are going to concentrate on the intermolecular force, which is the force between molecules. So you are having 2 molecules there. The force between them is intermolecular force. And we indicated that you have another force, that is the intramolecular force, that we indicated as interatomic force there. So you know that that's not what we are concentrating on. We are concentrating on the intermolecular force, which is the force between molecules. So we are saying these London forces are very weak. Intermolecular forces, and they are found in all the molecules. So you got to understand. But for alkanes, alkenes, and alkynes, you got to know that these ones, they have London force only. Their intermolecular force is London force for alkanes, alkenes, and alkynes, which are our hydrocarbons. We can move now to the second type of intermolecular force, which is our dipole-dipole. The dipole-dipole, we are saying, they are found between polar molecules or molecules in which there is an uneven distribution of charge, so that the molecule has a positive and a negative side. Let's look at this. We are saying here the oxygen is partially negative, the carbon is partially positive. So you are having 2 poles here. That's why we say dipole. You are having a positive pole and a negative pole, which becomes a dipole. That dipole, it has intermolecular force interaction with another dipole, because you will have your carbon as being partially positive and your oxygen as being partially negative. So that will refer to as dipole-dipole. That's why we're referring to these intermolecular forces as dipole-dipoles. Now you got to understand that these dipole-dipole, we find them in the haloalkanes, the aldehydes, the ketones, and the esters. So we're saying, I simplified it to you to say Hake, to say that is haloalkane, aldehyde, ketones, and esters. So you got to know that when you find at all times, when you found a haloalkane, aldehyde, ketone, and esters, you got to know that they have what we call dipole-dipole interactions, or the force between them, like intermolecular force, is the dipole-dipole forces. So that is the structure of the dipole-dipole, an example of dipole forces. Now we move to the last intermolecular force. So these ones, we refer to them as hydrogen bonds. Hydrogen bond, we found them between alcohol and carboxylic acid. Remember, we are talking about for the study of technical science. However, as you study further, you will learn that hydrogen bond can happen between a hydrogen and oxygen. It can happen between a hydrogen and nitrogen. It can happen between a hydrogen and a fluorine. But for our studies, we're going to limit ourselves to only the bond between oxygen and hydrogen. So we are saying that we will find them in alcohol and carboxylic acid. If we look at the structure of alcohol given here, which is a 2-carbon compound with an OH, because that's the functional group of alcohol. It's an OH group. The hydrogen of one alcohol will be bonded to the oxygen of another alcohol. So that forms what we refer to as hydrogen bond. So now our hydrogen bond, as indicated there, you will see that it's only one hydrogen bond that we find in alcohol. But when we move to carboxylic acid, we now have two sides of hydrogen bond. This is very important, learners. When you are writing your exams, you got to understand. When you find an alcohol, you'll be saying the alcohol has one side of hydrogen bond, but the carboxylic acid has two sides of hydrogen bond. So the two sides, you see that the carboxylic acid has COOH, it has two oxygens. All the oxygens serve as a side for hydrogen bond. So that's what we're saying. We're saying that at all times, know that the two oxygens will be sides for hydrogen bonding. So we're saying there are two sides of hydrogen bond. So at all times, you will know carboxylic acid will be stronger than alcohols, because alcohols have one side of hydrogen bond, whereas carboxylic acid has two sides of hydrogen bond. So it's very much important to understand this intermolecular force. Remember, we said we are dealing with physical properties. These physical properties, which you said is your melting point, boiling point, is your vapor pressure and viscosity. All of them, we are saying they have intermolecular. For us to be able to have our melting point, boiling point, vapor pressure, and viscosity, we must overcome the intermolecular force, meaning that energy is needed to overcome this intermolecular force. So as I recap, I'm saying to you, for carboxylic acid, more energy will be required to overcome the intermolecular force. Why? Because we have two sides of hydrogen bond. Whereas for alcohols, more energy will be required, but it will be less as compared to carboxylic acid, because it has only one side of hydrogen bond. Now, as we move to our intermolecular force, we're saying these are the intermolecular force of all the 9 different homologous series. Remember, we said we have 9 different homologous series that we are dealing with. The first ones I said is AAA, which is your alkane, alkenes, and alkynes, which are our hydrocarbons. For these ones, all of them, we are saying they have London force. Now, you got to know that London force are the weakest intermolecular force. They are the weakest intermolecular force. So you can see all the time what I'm doing. I'm identifying number one, the first I. I'm identifying the type of the intermolecular force. I'm saying that is the first thing that you do. Immediately when you get a question, what you're going to look at, you're going to identify the type of intermolecular force. If it's an alkane, alkene, and alkyne, you must be able to say the type of intermolecular force is London force. So at all times, you know that London force, we find them in alkanes, alkenes, and alkynes. So at all times, know that when you see alkanes, alkenes, and alkynes, which are hydrocarbons, know that they have London force. Now, this London force we are saying are the weakest intermolecular force. So these are the weakest intermolecular forces that we are having. So you got to know the strength as well. So if they are weak, it means the amount of energy that will be required will be least. So we're saying is the least amount of energy required. Remember, why do we need energy? To overcome the intermolecular force. So at all times, know that least amount of energy will be required if the intermolecular force is weak. So we are saying the first I there is for identifying the type of intermolecular force. At all times, when you're dealing with this question, physical properties, the first thing you will do, you will identify the type of intermolecular force. I indicated that when you have alkanes, alkenes, and alkynes, you know that they have London force. When you have haloalkanes, aldehyde, ketones, and esters, which I said is Hague, to make it easier for you to remember, those haloalkanes, aldehyde, ketones, and esters, those ones, they have dipole-dipole. But remember, I said all our 9 homologous series, all of them, they have London force. So it means the haloalkanes, all these molecules, all of them, they have London force and dipole-dipole. So when you find a question, you just check. If you're having haloalkane, you know that they have London force and dipole-dipole forces. When you're having aldehydes, you know they will have dipole-dipole forces. Ketones, they will have dipole-dipole forces. Esters will have dipole-dipole forces. Now, these dipole-dipole forces, when you look at the strength, because remember, we said you identify, after identifying the type of intermolecular force, you go now to compare the strength, the C, I said ice, so the C is for comparing the strength of the intermolecular force. So we are saying, immediately when you identify the type of intermolecular force, you are now going to compare the strength to say, for these ones with dipole-dipole here, we're saying they are stronger than London forces. Dipole-dipole are stronger, the dipole-dipole are stronger than the London forces, but are weaker than the hydrogen bond. So hydrogen bond are the strongest. So we remember what we said about the hydrogen bond? We said hydrogen bonds, they are found in alcohols and carboxylic acid. The difference, we said alcohols, they have one side of hydrogen bond. Carboxylic acid, they have 2 sides of hydrogen bond. So at all times, remember that when you see an alcohol, you see a 1 side of hydrogen bond. When you see a carboxylic acid, you see 2 sides of hydrogen bond. You will see when you do questions how you go about answering such questions. So I still emphasize to say the first thing you will do when you see an alcohol, you will identify the type of the intermolecular force to say it's hydrogen bond. For all these, they have what we call hydrogen bond. Now, carboxylic acid, they have hydrogen bond, but the difference is that alcohol has 1 side of hydrogen bond, and then carboxylic acid has 2 sides of hydrogen bond. I think I was very clear on that one. I emphasized. And we said immediately when you know what type of intermolecular force, you must know, compare the strength. So you compare, that is my C on my eyes there, to say you're going to compare the strength. We are saying for London force, they are the weakest. For dipole-dipole, they are stronger than London force, but they are weaker compared to hydrogen bond. For hydrogen bond, they are the strongest intermolecular forces. The last E there is for energy. Now, you must be able now to talk to energy, to say the amount of energy required. Remember we said the energy is required to overcome the intermolecular force. So the amount will depend on the strength of the intermolecular force. So what we are saying is that the amount will depend on the strength of the intermolecular force. Look, for example, when you're talking about alcohols and carboxylic acid hydrogen bond, we're saying more energy will be required to overcome the intermolecular force. So this table is your table to the exam. You take this one, you are carrying your memorandum as you go to exam, because you will identify the force. When you identify the force, you will check the strength of that force. When you check the strength of that force, you will check the amount of energy that is required to overcome those intermolecular force. Then you are able to answer questions. We are going to test this, whether we have understood or not. We are going to do a question based on that. Now, there are factors that influence these physical properties, our melting point, our boiling point, our vapor pressure, and viscosity. In real sense, in this question of physical properties, what we are dealing with here is that it's an investigation. So we have an investigative question that is saying, what is the effect of The first one will be, what is the effect of intermolecular force on the melting point, on the boiling point, on the vapor pressure, and on the viscosity? The second one will be, what is the effect of functional group on those 4 physical properties? What is the effect of chain length on those 4 properties? That's what we're going to talk about. What is the effect of molecular mass on those 4 properties? And what is the effect of branching, if we're having a branch or we don't have a branch? I've tried to make a short for you so that you can remember to say if chain mob, then you are able to see all those which are highlighted with red. That is the type of intermolecular force, the functional group, the chain, the molecular formula, and the branch. Because all these 4 physical properties, they depend on those 4. So the first thing you will check, what type of intermolecular force. You will check that is dependent on the functional group. You will check on the chain, whether it's a long chain or a short chain. You will check at the molecular mass. You will check at the branch. We're going to do examples that answer all that. So we're saying, when we talk about these factors, we're saying that type of intermolecular force, as we indicated, our AAA, our alkanes, alkenes, and alkynes, as indicated there, alkanes, alkenes, and alkynes, we said they have London force. We said haloalkanes, Hague, aldehyde, ketones, and esters. We said these ones, they have dipole, dipole. The last one, we said hydrogen bond is alcohol and carboxylic acid. You can see as the arrow indicates that as you increasing the intermolecular force, as you move from London force to dipole, dipole, the strength of the intermolecular force is increasing, meaning that more energy will be required as you move to the right, as you move towards hydrogen bond. Now, the type of functional group is important as well, because the strength of the intermolecular force depend on the type of functional group. So the type of functional group, for example, if you're having a hydroxyl group, it will be able to show the presence of hydrogen bond. So you're able to know whether you have hydrogen bond or you have no hydrogen bond by looking at the functional group. Now, the next factor is the chain length, which I just combine it with molecular mass, because as the chain length increases, the molecular mass as well increases. So we're saying as the length of the carbon chain or molecular mass in the organic molecules increase, the strength of the intermolecular force increases as well. As we move from methane to ethane to propane to butane, pentane, and hexane, you will see that the chain length is increasing. As the chain length increases, we are saying the melting point, the boiling point, and the viscosity will increase. Now, when the last one, we're looking at branch. When the number of branches increasing, more branches will result in the smaller surface area and lower strength of intermolecular force. So that's what we are saying. When you have more branches, the strength of the intermolecular force decreases. It becomes low. So you got to understand at all times. All the others, we were saying, when you have a longer chain length, the strength of the intermolecular force increase. When you have a higher molecular mass, the strength of the intermolecular force increase. But when you have branches, the strength decreases. So we must take note of that one, that when we have branches, the strength of the intermolecular force decreases. Now we look at the relationship between our melting point, boiling point, vapor pressure, and our intermolecular force. If we look, for example, we have a very nice example here, where we are given butane, pentane, and hexane. Those three are organic molecules: butane, pentane, and hexane. If we look at the boiling point of butane, you will have minus 0.5 degrees Celsius as the boiling point. And for pentane, you will have 36 degrees Celsius. For hexane, you will have 39 degrees Celsius as the boiling point. So you can see that the strength of the intermolecular force increases as the carbon chain increases. You can see we're moving from 4 carbons, 5 carbons, 6 carbons. You can see that the carbon chain is increasing, or the molecular mass is increasing. As it increases, even the melting point, boiling point, and viscosity increases. You can see that there is no vapor pressure, because with vapor pressure, as the strength of the intermolecular force increases, the vapor pressure will decrease. Hence, we gave example there to say increasing strength of intermolecular force, decrease vapor pressure. So of all the 4, you got to take note of vapor pressure, because with vapor pressure, as the strength of the intermolecular force increases, the vapor pressure decreases. So now let's look, for example, the same. We have butane with given there with a vapor pressure of 204. We have propan 2O with a vapor pressure of 24.6. we're having again propanol with 2 and ethanoic acid 1,6. Now, if you can look there, you will be able to see that butane, remember what we said, the I's. Butane, what is the type of intermolecular force? The type of intermolecular force for butane, because those are alkanes, we said is, so that is the first thing that you will do. You look at the I, you go to the C, you go to the E. So you say, what is the type in butane? You said, no, here we find only London forces. In butane, we find London forces. London forces are the weakest. They are weak intermolecular force. So you know that, okay, it's London force, and London force is weak. So since we are having London force and London force is weak, less energy is required. You see, you are still doing the I's now. You are saying the first thing, you identify the type of intermolecular force. You compare the strength of the intermolecular force. You talk about the amount of energy required. Remember, when you talk about energy, you must mention that it's energy required to overcome the intermolecular force. For butane, less energy is required, which means vapor pressure will be very high. Remember, we said for vapor pressure, as the strength increases, you see the strength is increasing from butane to propan to one. The strength is increasing because we are moving from London force, propan to one. What is the intermolecular force? Dipole-dipole. So you are able to see that, okay, as we move now to dipole-dipole, the strength of the intermolecular force is increasing or is stronger than for alkanes. So when you are having these ones, which is your ketone now, you are having dipole-dipole, then the vapor pressure decreases to 24.6. And as we move to propan-1-ol, remember what we said about propan-1-ol, which are alcohols. We said alcohols, they have the strongest intermolecular force. So you see that it decreases to 2. But as you move to ethanoic acid, it decreases to 1.6. Why 1.6 now? Because when you go to ethanoic acid, we said it has 2 sides of hydrogen bond, and propanol has 1 side of hydrogen bond. Hoping you have understood this, because this is very, very important. We indicated on this one that increasing strength of intermolecular force will increase the melting point, will increase the boiling point, will increase the viscosity. And we said increasing strength of the intermolecular force will decrease the vapor pressure. So as all of the other 3 increases, vapor pressure decreases. Now let's look at a nice example there. We're having example number 1. We're saying there, boiling and melting points of organic compounds increase with increasing strength of intermolecular force. More energy is needed to overcome the intermolecular force. You are going to apply the same I's that I referred to. You see, I've used it very much, so I hope it's going to help you to answer the questions. We said the first thing, look at pentane. We're given pentane there. You look at it, you say, this is a hydrocarbon, which means hydrocarbons, all of them alkanes, they have London force. So you will still follow the same module that I've been talking about, which is now you will identify the type of intermolecular force. So you are saying this is London force. Then when you look at the melting point, it's minus 130. When you look at the boiling point, it's 36 degrees Celsius. So you can be able to see that, okay, that is for pentane. Let's go to pentanol, which is now an alcohol with a hydrogen bond. That we said is the strongest intermolecular force. So what is going to happen? The melting point is minus 90 degrees. The boiling point is 118 degrees Celsius. You can see the increase from 36 to 118 of the boiling point, and the increase of the melting point from minus 130 to minus 90. Take note of the negative there. Minus 130 is less as compared to minus 90 degrees Celsius. So you can see that the first thing you will do, you will identify the intermolecular force. You say pentane. Pentane has, then you are able to talk about pentane, or it has London force. You go to the C, you compare the strength. You say, okay, London force are the weak intermolecular force. You can't write IMF, only me can write IMF, you'll write intermolecular force. So it's weak intermolecular force. Now, energy, you know, less energy. Already you know, that is about pentane. You are able to write everything. From there, you can talk now about pentan-1-ol, which is an alcohol. Pentan-1-ol, you are able to look at it as well. You say, what is the type of intermolecular force? You know that is hydrogen bond. You'll write hydrogen in full. I don't have much space here, so I'll just write in short, hydrogen bonds. So you find hydrogen bonds in pentanol. So pentanol has hydrogen bond. Now you have seen that, okay, we're having our pentanol with hydrogen bond. Is it weak? No. That is the strongest intermolecular force. So that's how you answer these questions. So they become very simple because you'll be enjoying yourself. You are just identifying the type of intermolecular force. You check the strength to say what is the strength. You say this is the strongest intermolecular force. And if it's the strongest, how much energy? You say more energy will be required. So always you look at the strength. When the strength of the intermolecular force is weak, you know less energy. When it's strong, you know more energy will be required to overcome the intermolecular force. Language here is of importance, learners. So as you do this, make sure that you talk the correct language so that you are able to get all your marks. So I was able to show you, using this nice example, how these intermolecular forces affect our physical properties. Now, that is an activity. This activity, if you look at it, they're saying the melting points of 4 different straight chains. So these are hydrocarbons, all of them. They're telling you that those are hydrocarbons. So that is the first thing. You must be able to read the question and understand it. So they are saying these hydrocarbons, straight chain hydrocarbons are given. Their melting point given, minus 182.5, minus 95, 28, and minus 56.5. They say which hydrocarbon has the strongest intermolecular force. So you go to look there and say, okay, when the strength of intermolecular force increases, the boiling point increases, which means you look for the one that has the highest boiling point, which is your Roman figure 3, that is number C. Now, as we move to the second activity, I'll just talk to it as I pass. Now, to say now, you must be careful here. You are given a statement, a nice question. They're saying define the term boiling point. You will define the boiling point. They said what is the relationship between strength of intermolecular force and boiling point? We said when the strength of intermolecular force increases, the boiling point will increase. So you will get that correct. Now, a nice table is given. We are given compounds, which is our organic compounds. We have propane, we have propanone, we have propanol, propanoic acid. You can see we are given London force, we are given dipole-dipole, and one side hydrogen bond and 2 sides hydrogen bond. So you are able to see the boiling point is increasing as you go down, as you move from A to C. So you see that, okay, as the strength of the intermolecular force increases, the boiling point increases, which is the question they asked in 2.2. Now, they are saying refer to the type of intermolecular force to explain the difference in boiling point. So they said between compound A and B, you'll use the I's. You'll say A, what type of a force do we have? What strength of the intermolecular force? The amount of energy. You say B, what type, and all that. Then you are able to get all your marks with no problem. Now we move this is the question paper they wrote in June last year. So last year they wrote this paper, those who are writing supplementary exams. Question 3, it was in question 3. We are hoping that it will remain there. Now we're saying 3 carbons, A, B, C, were used in investigation to determine the effect of branching on vapor pressure. Look at this one. Number A, you are given a structure, a long chain, no branches, just a long straight chain with 4 carbons. Remember, 4 carbons, we said it will be butane. So you will remember that this will be butane because it's 4 carbons. Now, 1, 2, 3, 4, 5. I beg yours. So we have 5 carbons. It's important in the exam that you ensure that you count the number of carbons correctly, because now this structure now is a structure of pentane because we are having 5 carbons, not 4. Now, if we look at number B, we are having 4 carbons and a methyl group in carbon number 2 there. So this is 2-methyl butane, which is an isomer of that one. And we have another isomer, which is 2.2 dimethyl propane. You can see that the number of branches is 0 branch here. There is no branch there. Here we have 1 branch. Here we have 2 branches. Remember what we said about branches? As the number of branches increases, the strength of the intermolecular force decreases. And you know that as the strength of the intermolecular force decreases, the vapor pressure increases. That's why you see the one with the lowest strength, in terms of the strength of intermolecular force, the lowest one has the highest vapor pressure. Because when you're dealing with vapor pressure, we said when the strength of the intermolecular force is the least, you have the highest vapor pressure. So understand that one. That was a question they wrote in June 2019. At the end of the year last year, they wrote this question paper, November 2019. Now, if we look at this paper, they said the table below shows 2 organic compounds with their corresponding boiling points. You can see you are given now a butane now that I was talking about. You are having a 2-methyl propane. So you can see 0 branch, 1 branch. You have a 0 branch and a 1 branch. So you must be able now to know that you have those branches. What is happening at the boiling point? You see that as the branches, as now you have a branch, the boiling point decreases, which shows that the strength of the intermolecular force decreases as the number of branches increases. So these questions were asked in the exam. So hoping if they come again, you will do well. Those were the type of questions which they asked. They asked to define the melting point and all those questions without wasting time. So that's all I can say in terms of our physical properties. So stick to our eyes, ensure you know all the intermolecular force, ensure you know how to compare the strength of the intermolecular force, ensure you know the energy needed to overcome the intermolecular force. So we are now moving away from this part. We are moving to the next one, which is our reactions of organic molecules. For the reactions of organic molecules, what we are going to do, we are going to deal here now with chemical properties. Remember, we're dealing with the physical properties. Now, with the chemical properties, we are saying it shows this is the reaction with other molecules. When we have that, we are saying that chemical change, new substance is produced. Remember, when you're dealing with physical properties, the molecule did not change. You remained with your water. What was changing was it was in a solid form, in a liquid form, and in a gaseous form. However, during chemical change, the new molecule is formed, which means it changes. You no longer have what you had before. So we're going to look at esterification. We're going to look at substitution, addition, and oxidation. So those are the reactions that we're going to look at, 4 of them. Without any wasting of time, we are going to look at esterification. To say for your esterification, you will need an alcohol and a carboxylic acid. So you will have an alcohol and a carboxylic acid that will form ester and water. But there is a catalyst that we use, which is sulfuric acid. So it's very much important you know that here, because we are going to react an alcohol and a carboxylic acid to form an ester and water, we are saying we're going to use sulfuric acid as a catalyst. Why sulfuric acid? It's a good dehydrating agent. It's able to remove the water. Now, let's look. Remember, as the reactions take place, we are here focusing on the functional groups, the 2 functional groups. The functional group of alcohol is OH. The functional group of carboxylic acid is COOH. So you got to see that we are focusing on those when we have our esterification reaction. So what is going to happen is that the hydrogen, the ones in black, the hydrogen from the alcohol will combine with the OH from the carboxylic acid to form our water molecule. So those will be formed. So look, carboxylic acid has 2 oxygens, so we take 1. At least we are trying to be fair. Now, from the alcohol, we don't take oxygen, we take the hydrogen. So we combine them, we form water, then we have our water that is formed. Then we have a new bond that is formed, which is what we refer to as the ester bond that is formed between the carboxylic acid and the alcohol. Now, the alcohol, which was methanol in this case, it becomes an alkyl group. So an alcohol becomes methyl. Methanol becomes methyl. Why methyl? We said methyl is when you are having an alkane with running short of 1 hydrogen. So you know methane as CH4. This one is CH3. So that becomes our methyl. The structure that goes with the C double bond O, that is the parent chain, our parent chain now, which is now methanoate. Methanoate, you are saying, is a methane. So in esters, we are saying you look at the number of carbons, is 1, you know it's for methanoic acid. Then you are going to say methanoate at the end of the name. So it becomes methyl methanoate. So we're saying it's an alcohol and a carboxylic acid. In the presence of sulfuric acid, they form an ester bond and water. and we are saying the alcohol becomes an alkyl. So from methanol, you'll get methyl. From methanoic acid, you will get methanoate. So that is very much important as you look at esters. Now, the next reactions are the substitution reaction. Remember, I said we're going to do esterification, we're going to do substitution, we're going to do addition, and lastly, we're going to do oxidation. So if we look at substitution, as the name says, like substitution in any game, it can be rugby, it can be soccer. When you substitute, the other player goes in, the other player goes out. So you got to understand here that we are going to have the chlorine that is bonded to the chlorine is going to react with methane there. What is going to happen is that we're going now to substitute one chlorine there. We'll be substituting one hydrogen there. So that's what will happen. So we are saying you substitute, you take my place on the bench, I take your place in the playing ground. So that's what is happening. The chlorine will substitute and take the place of the hydrogen. The hydrogen will take the place of the chlorine. So we will have two things that are formed there, which is our haloalkane and our hydrochloric acid. So what is happening is that we have two reactants that reacts together to form two products at the end of the day. So now what we are saying here during this type of substitution reaction, we are saying we call it halogenation because we are substituting, we are using halogen to substitute. Hence we refer to it as halogenation. Now, this halogen that is formed, all the halogens that are formed, you can now add water. You can substitute now using water, or you can substitute using potassium hydroxide, which is our dilute strong base. So we are saying two reactions that can take place from our chloroalkane that we got from the first reaction, which is halogenation. It is your hydrolysis reaction. So we're saying there are two hydrolysis reactions that we are looking at. We are using water and mild heat. We can use potassium hydroxide and mild heat. This potassium hydroxide, it can as well be lithium hydroxide or sodium hydroxide, but it must be dilute, because if it's not dilute, the reaction can take a different path. So we're saying dilute strong base and mild heat are used when you're using sodium hydroxide, potassium hydroxide, or lithium hydroxide. So they're going to substitute with the bromine. So these two reactions where you're using water or potassium hydroxide, we refer to them as hydrolysis. So we're saying the chlorethane, which is the chloroalkane, or the haloalkane that is formed in reaction number 1, which you said is halogenation, can undergo two other reactions, which are called hydrolysis. We can use water and mild heat. We can use a dilute strong base and mild heat, as the reactions are shown there. You can see as well, we're going to have now that bond. We're going to have the OH replacing the chlorine. You can see the OH there. It has replaced the chlorine, and the chlorine has replaced the OH on the water molecule. So now you can see that is substitutions, because two players in, a player in, a player out. That's what happened there. So all these two reactions, so you know substitutions, we're saying the first reaction that we talked about is halogenation. However, there are these conditions. It means these conditions are necessary for this reaction to take place. There must be sunlight. If there is no sunlight, the reaction won't take place. For the second reaction, hydrolysis, all of them were saying mild heat. However, when you are using dilute strong base, we are saying you must be able to, if you are using a base, it must be a dilute strong base. So those are first three substitution reactions that we have formed. You can see where the Br was, we now have the OH there bonded to that one. So there must be a hydrogen there. So you are having bromine and hydrogen, OH there, having replaced one another. Now, we move to the last type. We can take now this alcohol and add and substitute with a halogen again. Look, we're having HX. You know X stands for halogens, which is our bromine and our chlorine for this case. So we can have this reaction. It can take place. If we are having a tertiary alcohol like this, the reaction can just spontaneously take place, and we'll have the X replaced with the OH, then it's able to form our water. But now, when we are having the other halogenation, if you are having a primary alcohol, you must be able to add heat. So remember, we said there are I talked to 4 substitution reactions. The first one was halogenation. We had 2 hydrolysis and 1 halogenation. So we're saying halo, high, high. So you can see that you have two halogenations and two hydrolyses under substitutions. What is important here, for each reaction, you must know the conditions, the special conditions, what is needed for that reaction to take place. Now, that is substitution. Now, let's go to addition. Addition reaction, as the name said, we are simply adding. That is addition, we are simply adding. So what is happening here is that we are going to add a halogen, which is a Br and a Br. When you add, all times you are adding where there is a double bond. So all the time you look for where there is a double bond. That's where your addition will occur. Your addition will occur where the double bond is. So each bromine will go and add where in each carbon that are in the double bond. So that one we call it halogenation, because we are adding halogens. When you are adding hydrogen, the reaction will be referred to as hydrogenation, which has the catalyst, which is platinum, palladium, or nickel. So you must know at all times that when you are having a double bond, you will have addition type of reaction. So you have seen that, and we are saying no catalyst for the halogenation, but for hydrogenation, you need a catalyst, or you need your special conditions, which is your platinum, palladium, or nickel. Now, another hydrogenation, you can have hydrohalogenation if you are adding a hydro and a halogen. So the reaction is referred to as, so you just look at what is being added. It will tell you the type of addition. So what is important here, what we are saying, is that for addition, you are going to need unsaturated, which means there must be a double bond. There must be that double bond. When you see a double bond, you know it is going to undergo, the double bond is going to become saturated. And that reaction, we're going to refer to it as addition. So we're saying, in short here, USA. So when you want to remember for addition reactions, you know it's unsaturated that react to form saturated. You can see that the product is saturated now. There is no more double bonds. It's saturated, single bonds only. Now, when you look at this, the next reaction, which is hydration, we're using water. Remember, we're using water last time. We said we'll use sulfuric acid as a dehydrating agent. We're using water even here. We use the concentrated sulfuric acid or phosphoric acid as our catalyst. So it's very much important for hydration. It means we're adding water. So we're saying hydrohalogenation, hydration. The next reactions. So those are the four reactions that we talked about under addition reactions. So we're saying under additions, we know at all times that we add where there is a double bond. Where there is a double bond, that's where the addition reaction is going to take place. Hydrogenation, halogenation, we talked to those. We talked to hydrohalogenation and hydration. As you can remember, for addition now, we're saying now is 1 halo and 3 high. So those high hydration, hydrogenation, and hydrogenation. The first one was halogenation. So those are 4 addition reactions. What is of paramount importance? Remember as well that we use the catalyst. What are the catalysts that are being used? Now, the last type of reactions that we are having is our oxidation or combustion reaction. Now, on these ones, what is happening is that we are having our alkanes. Our alkanes, they are reacting with excess oxygen to form carbon dioxide, water, and energy as well is given off. So that is very much important. You are having an alkane, you can see we are having methane there, reacting with oxygen to form carbon dioxide and water. So that will give you now all the time. So for oxidation reactions, simplest. When you see the reaction, you know it's an alkane plus oxygen. You know already the products are carbon dioxide and water. What is left for you is to balance the equation. Ensure that the equation is balanced at all times, as we have done with methane. I will use it as an example to say methane, you have CH4. How many carbons? 1 on the reactants, 1 on the product. So the carbons are balanced. How many hydrogens? 4 in the reactants, and hence we wrote a 2 there in red to balance the hydrogens, so that 2 times 2, they become 4. The hydrogens are balanced. From there, you check the oxygens. How many oxygens? We have 2 plus another 2, that is 4. Hence, we wrote a 2 there to balance that. So ensure that you do that. But the most important thing, know that during oxidation or combustion, you form carbon dioxide and water, then you are able to balance. If you are unable to balance, at least you will have got 2 over 3 marks. But ensure that you get all the 3 marks. as we do that. Last year in June, that is the paper that we had in the June exam. They gave them that diagram. Already I said, when you see an alkene, you know that the reaction is going to be addition. We add. When you see alkenes, you know they are unsaturated. Hence I said USA. We are saying unsaturated is forming saturated. So the reaction is addition. So you know already that reaction B will be addition. You will know already that reaction A will be addition because it's coming from an alkene. So all the time when you see alkene, you are seeing that this must be addition reaction. Now, what type of addition? Because that is the next question. The first question is, what type of reaction? We said it's addition. Why is it addition? Unsaturated was forming saturated. Now, what type of addition? This one, you can see that we've added hydrogen. So that is hydrogenation. What type of addition? We have added HCl here. You can see that is halogenation. You can see that this is saturated. It's forming another saturated. So you must know that it's USA and triple S. For triple S, what we are saying for triple S is that saturated forming another saturated, that is substitution reaction. So we are 100% together there. You can see that how to identify the type of reaction. In November last year, that is another question. Already, you can see we're having a double bond there. You know we're going to undergo addition type of reaction. What are we adding? Is HBr. You know is hydrohalogenation. Hydrohalogenation, you know is addition reaction. Knowing that now you are having your hydrogens and your bromine going to bond there in carbon number 2. So you will know the answer to that one will have been 2-bromobutane. Now, as you move now, you are adding the H2. You know that is hydrogenation. Hydrogenation, we talked about it. We said now you will form an alkane from but2-ene. That will be butane. So you know that we have able to move from that to that. That was from last year's exam. Those are the questions that they've asked. Now, without any